Digital modulation. There are three main types of digital modulation. First, we have amplitude shift keying, or ASK. Then, we have the frequency shift keying, or FSK. Lastly, we have the phase shift keying, or PSK. And then there is a special type of digital modulation which is known as quadrature amplitude modulation, or QAM. Basically, this is just a combination of ASK and PSK. Let's start with amplitude shift keying. Amplitude shift keying is the simplest digital modulation technique where a binary information signal directly modulates the amplitude of an analog carrier. Similar to a standard amplitude modulation, or AM, except that there are only two output amplitudes possible. This is sometimes called digital amplitude modulation, DAM, continuous wave modulation, and on-off keying, OOK. Mathematically, amplitude shift keying is expressed in this equation. V sub ASK of t is the amplitude shift keying wave. Vm of t is the digital information, or the modulating signal, in volts. A over 2 is the unmodulated carrier amplitude, also in volts. And lastly, we have omega c, which is the analog carrier radian frequency. Its unit is radian per second and has the formula of 2 pi f sub c. The modulating signal, Vm of t, is a normalized binary waveform, wherein if it is a logic 1, positive 1 volt will be its value, and if it is logic 0, negative 1 volt will be its value. Therefore, for a logic 1 input, Vm of t will be equal to positive 1, and the equation will be reduced to A cosine omega m of t, because the denominator of A, that is 2, and 1 plus Vm of t, which is 1, will be equal to 2, so it would cancel out. What remains is that A cosine omega m of 2. That would be the equation for VASK when logic is 1. On the other hand, when logic is 0, Vm of t would have a value of negative 1. And then since the first term is 1 plus negative 1, the whole equation would just equate to 0. So during logic 0, VASK of t is equivalent to 0. Therefore, no waveform is present when logic is 0. This is an example of an ASK signal. As you can see, there are 5 bits in this image. 1, 0, 1, 1, 0. When the bit is 1, there is a sine wave. When the bit is 0, there is no waveform. Basically, the amplitude is just 0 for bit 0. Now, one signal element accounts for 1 bit. So the baud rate for the entirety of this signal, which is 1 second, is 5. Meaning 5 signal element in 1 second. Also, one signal element is equal to 1 bit. So the bit rate is also 5, because the duration of this waveform is 1 second. Let's take a look at how this occurs. First, we have our digital signal. This is our modulating signal. And then we have our carrier signal, which is just a simple sine wave, analog in nature. Both will have to pass through the multiplier, and both signals will be combined to produce an ASK signal. As you can see, when the bit is 1, meaning the logic is high for our modulating signal, when it is combined with a carrier signal, the ASK signal would result in an amplitude and a frequency equal to our carrier signal. But when the bit is 0, our modulated signal will have no waveform. The amplitude is just equal to 0. That is why this is also called on-off keying. It's either there is a waveform or there is no waveform. Bandwidth. This is the formula for the minimum bandwidth necessary to pass n bits. Bandwidth is equal to f sub b divided by n, wherein f sub b is the channel capacity in bits per second and n is the bits encoded into each signaling element. Now let's take a look at Baud. Since Baud is the encoded rate of change, it also equals to the bit rate divided by the number of bits encoded into one signaling element. Thus, Baud is also equal to f sub b divided by n, wherein f sub b is the channel capacity and n is the bits encoded into each signaling element. Let's take a look at an example. Determine the baud and minimum bandwidth necessary to pass a 10 kilobits per second binary signal using amplitude shift keying. For ASK, n is always equal to 1, and the baud and the minimum bandwidth are determined from the equations that we have seen before. Excuse. So we have B is equal to f sub b, that is equal to 10 kilobits per second in this example, divided by n, that is always 1. So we have 10 kilohertz or 10,000 hertz. And for baud, it is always equivalent to our bandwidth, because we also have the same formula, f sub b over n. F sub b is 10 kilobits per second divided by 1, so the result is also 10,000 baud. Now, the use of amplitude modulated analog carriers to transport digital information is relatively low quality. Low cost of digital modulation and therefore is seldom used except for very low speed telemetry circuits. Frequency shift keying. Frequency shift keying is a relatively simple, low performance type of digital modulation. This is a form of a constant amplitude angle modulation similar to standard frequency modulation, except the modulating signal is a binary signal that varies between two discrete voltage levels rather than a continuous changing analog waveform. It is sometimes called binary FSK or BPSK. This is an example of a frequency shift keying signal. As you can see, we still have our example of 10110, 5 bits in 1 second. So the bit rate is 5. One signaling element accounts for 1 bit, so the baud rate is also 5. And let's take a look at the waveform. In here, there are two frequencies. When the bit is 1, a high frequency waveform occurs, but when the bit is 0, the waveform becomes low in frequency. Let's take a look at how the BPSK is generated. In the first waveform, we have our digital signal, 10110. It will pass through a voltage-controlled oscillator, a VCO, which is a simple circuit in which the frequency of the generated output is dependent upon the voltage of its input. Now, since our input only has two voltage levels, either any finite positive value and 0, it only has two output frequencies. As you can see, when the voltage is high, the frequency is also high. And when the voltage is 0, the frequency is low. This is the mathematical expression for the frequency shift keying. VFSK of t is our modulated signal of FSK. V sub c is the amplitude of the carrier voltage. The carrier center frequency, F sub c, is shifted or deviated up and down in the frequency domain by the binary input signal, or our digital signal. As the binary input signal changes from a logic 0 to a logic 1 and vice versa, the output frequency shifts between two frequencies, a mark or logic 1 frequency, abbreviated as F sub m, and a space or logic 0 frequency, abbreviated as F sub s. By the way, mark and space are other terms for logic 1 or logic 0 and logic high or logic low. These aren't only exclusive for FSK. It can only be used in other digital modulation schemes. Now let's proceed. The mark and space frequencies are separated from the carrier frequency by the peak frequency deviation delta f, and from each other by 2 delta f. Frequency deviation. Frequency deviation is the difference between either the mark or space frequency and the center frequency, or half the difference between the mark and the space frequencies. It is given by the formula delta f equals the absolute value of the mark frequency minus the space frequency divided by 2. Usually the mark frequency is higher than the space frequency, so this would yield a positive value even without the absolute value. FSK bitrate, Baud, and bandwidth. The time of one bit, T sub b, is the same as the time the FSK output is a mark of space frequency, T sub s. The bit time equals the time of an FSK signaling element, and the bit rate element equals the Baud. So Baud is given by the equation F sub b over n, but n is also equal to 1 for FSK, so we have Baud is just equal to F sub b. The minimum bandwidth can be approximated as this equation. B equals 2 times the quantity of delta f plus F sub b. Now let's take a look at an example. Determine the peak frequency deviation, minimum bandwidth, and Baud for a binary FSK signal with a mark frequency of 49 kHz, a space frequency of 51 kHz, and an input bit rate of 2 kbps. As you can see in this example, the space frequency is actually higher than the mark frequency. And we also have a given of input bit rate. Now, first, let's solve for the peak frequency deviation. The peak frequency deviation is determined by the equation delta f equals F sub m minus F sub s divided by 2. So we have 49 kHz minus 51 kHz. It's equal to 2 kHz divided by 2. So delta f, or the frequency deviation, is equal to 1 kHz. Next, let's determine the bandwidth. This is how we approximate the bandwidth for FSK. B equals 2 times the quantity of delta f plus F sub b. So we have bandwidth is equal to 2 times the quantity of 1000 plus 2000. So bandwidth is equal to 6 kHz. Lastly, we have to determine the Baud. So to determine the Baud, we have Baud equals F sub b divided by n, but n is equal to 1 for FSK, so we have Baud is equal to 2000 divided by 1, so we have 2000 Baud. Continuous phase frequency shift keying, or CP-FSK. CP-FSK is a binary FSK, except the mark and space frequencies are synchronized with the input binary bit rate. The mark and space frequencies are selected such that they are separated from the center frequency by an exact multiple of 1/2 the bit rate. So we have the equation f sub m and f sub s are both equivalent to n times f sub b divided by 2, where n may be any integer. This is an example of a non-continuous frequency shift keying. As you can see, we have f sub s and f sub m, and the transition between the mark and the space frequency, there exists a discontinuity in phase of the waveform. So when this happens, the demodulator has trouble following the frequency shifts, and error may occur during the demodulation process. This is what we are trying to avoid for continuous phase frequency shift keying. Now this is an example of continuous phase frequency shift keying. As you can see, the transition from logic 1 to logic 0 is very smooth. CP-FSK has better bit error performance for a given signal-to-noise ratio. However, it requires synchronization circuits, making it more expensive to implement. The last, we have phase shift keying, or PSK. PSK is another form of angle modulated constant amplitude digital modulation. MRE digital modulation scheme similar to a conventional phase modulation, except with PSK, the input is a binary digital signal and there are a limited number of output phases possible. Binary phase shift keying, or BPSK. BPSK is the simplest form of PSK, wherein n is equal to 1 and m is equal to 2. Other names are phase reversal keying, or PRK, and biphase modulation. This is a form of a square wave modulation of a continuous wave signal. Now for binary phase shift keying, there are only two phases, one for each logic input. So for logic 0, output phase is 180 degrees, and for logic 1, the output phase is 0 degrees. This is an example of a BPSK waveform. So we have our input binary waveform. On the top, there are 6 bits, 1, 0, 1, 0, 1, 0, alternating bits of 1s and 0s. And our BPSK output, as we can see on the bottom waveform, for bit 1, we have our unshifted sine wave, which has the expression sine omega c of t. And then for bit 0, we have our shifted sine wave. It is shifted 180 degrees. Therefore, it has the expression negative sine omega c of t. And then when the following bit is 1, so we have to shift the phase back to 0 degrees. So it again has the expression sine omega c of t, and so on. So basically there are only 2 phases for 2 of the bits. And that's it for digital modulation